Alright, good morning. So what have we done this unit so far? So far we've looked at force of gravity. So that's a force down acting on some mass. So we know mass is kilograms, but we know the force is the mass times acceleration, or 9.81. So that's in kilograms. Our force is in newtons. So we kind of did a unit on that. And then we also looked at friction forces. We did a few labs on that, and we kind of looked at if you're dragging something or a box along a ground, you have a pushing force, but you also have something working backwards as well. So if you're pushing this way, you work backwards, and there's some force of friction. And then that's where our force of friction equals some mu, which is between 0 and 1, and our normal force, which is always perpendicular with your surface. Alright, so then after that we worked on 2D friction forces. That's kind of the same as that, but a lot more complicated because you're working on slopes. So that's when we had a box and we were pushing upward, and we had a force of friction working against the box, but we also had a force of gravity in the x direction also working against our box. So we had to calculate that using a triangle like that. So we kind of worked on that in another lesson. And then after that we worked on Hooke's law, which pretty much says that if you have a spring or anything, the amount it stretches is proportional to the amount of mass, or the amount of force of gravity that it has. So more stretch for a heavier, and that's where we had F equals kx, where k was our constant. And then we have a tension force here, was pretty much where we have ropes. And the tension of the rope is the force of the rope. In most of our questions it was just the same as force of gravity of your mass and how much gravity is on that. So we have tension forces in 1D only. We were going to go into 2D, but we're going to scrap that now, and you would see that in Physics 12 anyways, so we're only going to do 1 dimensions for tension forces. Alright, so our force of rope and our mass here. Okay, so that's what we've done, and that's what we've seen so far. So that's this unit so far. Our last thing that we have to work on is kind of Newton's laws. So we have to see Newton's laws 1, 2, and 3. So what we're going to look at right now is the third law first, which is a little strange. So I'm going to flip that over. So that was this is Newton's third law. Okay, Newton is a scientist that lived way back in the day, and he came out with 3 really famous laws that describe how forces work. So we'll go through just our page here on Newton's third law. I think it's the easiest law, or the simplest, not really any calculations. So let's go through the first thought. If you wish to climb a stairs, which way do you move? So we have a flight of stairs here, and we have someone climbing this stairs here, and the person's going up, right? But if you think about it, which way are you pushing? The foot is pushing down, but the person is going up. Okay? So overall, you move up, but you're pushing down. Okay? So if you think about that, that's opposite directions. Now let's look at this person rowing their boat with an oar. So if they want to go forward, which way do they push their oar backward? Or do they push their oar? I already gave the answer. They push it back. So they push back, but which way does the person and the boat go? They go forward. So again, it looks like the way you push makes you go the opposite way. So now, after getting these two ideas in your head, we can go and read what the third law is. It says, if two bodies interact, the force the first body or the person exerts on the second body, the water, will be equal and opposite the force that the second body, the water, exerts on the person, the first. The two forces will be opposite and equal. So it says if you put a force on something, it's going to put that same force back on you. Okay, so any force. You kick a soccer ball, the soccer ball kind of kicks you back. You push on the desk pushes back. So that's kind of the idea. It's called the law of action and reaction. So overall here it says the dog runs on a floating log to the right. So the dog's running that way. That means its feet are pushing backwards on the log. Okay. So normally if it was cement, the dog would go forwards by pushing backwards because the cement is not moving anywhere. But this time the log is floating in water and there's not really that static solid object. So here it's pushing backwards, but the log doesn't really push back on it in this case. The log will actually start moving to the left, and the dog will not actually move because there's not enough friction or static of the log. So overall you would have the dog not moving, my really good dog here, and the log would actually go to the left because it never put the force back on the dog. The reason why is because there's water and it's not actually on something solid. Okay, so overall the dog doesn't move. And since the log is not held in place, it doesn't, the dog doesn't move. Alright, so now let's look at this next example here. It says if you have two spring scales attached to a rope, so you have two spring scales attached to a rope, you're going to pull the rope so that you keep one scale still. So I'm going to keep this one still and I'm going to pull on the other one to see what happens. Okay, so overall if I pull on the one, I'm pulling on the other one, but it says this green one moves as well. So it says 4.5 newtons right now, and the one that I pulled on also said 4.5 newtons. So I'm pulling on the red one, and the green one I didn't move, but they both say the same amount of force. Okay, but my right hand was the one applying the force. Okay, but in reality the rope is not moving, and so since the rope doesn't move, your left hand, or my left hand here that's holding the green one, has to also intuitively put a force to the left, keeping it there. Okay, even though I said I'm moving my right hand, I'm also moving my left hand intuitively. Okay, there's no way to keep this rope still without moving both in opposite directions. Okay, so overall it says take a spring scale and attach rope, pull on the second scale while keeping the first one still. What happens? Both register the same force, which is interesting because I would think only one would register the force, the one applying it. But again, if you apply a force, that means something should move, because force is mass times acceleration. So if you apply a force, it should move or it should accelerate. So that means if it's not moving, there must be an equal force in the opposite direction. Okay? So equal on both sides. Alright, so now we're just going to flip to this back page, almost done here. So now you wrap a rope around a tree. And you pull on it with 500 newtons. It says, what is the tension of the rope? So you're pulling 500 newtons of force on the rope. Okay? But again, if you do any amount of force, something should move. So since the rope is not moving, that means there must also be 500 newtons of force being pulled to the left by the tree. Okay? So overall, the tension of the rope is just this 500 newtons. And it has a force being applied to the right of 500 newtons, but also to the left of 500 newtons. So overall, our tension of the rope is this 500 newtons that is being applied. But it's interesting, it's not 500 plus 500, it's just the 500 overall as your tension. Alright, now this next example, we have two people pulling on the rope. Just like this example, the rope is not moving, and this person on the right is pulling by 500 newtons. If this person does not pull back, then they'll both go to the right, because force has to accelerate something. So that means if it's not moving, this person is also pulling at 500 newtons to make it not move. So what's the tension of the rope? It's this 500 newtons. Again, it's the overall tension of the rope. So if you don't want to move it, it's not 500 plus 500, it's just 500 overall. It's not moving, so that means they have 500 on both sides. Okay, last question. I kind of added this one. A bowling ball hits a pin. What exerts more force? You have a bowling ball and you have a pin. It hits the pin, and the pin goes flying. Okay, but that moment that it hits this pin, the bowling ball exerts a force to the right, a pretty high force. That pin does the same exact force back at it. Okay, but you all know that the pin would go flying. Okay, so overall, both forces would be the same. The bowling pin would go flying, but this is more to do because of momentum. And we don't really go into momentum in grade 11. We're going to go into this into grade 12. Okay? All you need to know is that any object that hits some other object, they'll apply the same exact force to each other. Okay? The bowling ball in this instance will still go to the right, so it won't feel it as much as the pin would, because the pin is still, but changes direction really quickly once that bowling ball hits it. Okay, but that's more so momentum. Again, we won't cover. All right, so that's Newton's Law 3. We have a YouTube here if you want some extra something to watch to help you out. All right, thanks for watching.